Hello, my name's Max, and I'm here to talk about coroutines in Kotlin, as well as some specifics relating to using them with Kotlin Multiplatform. So first of all, why am I even giving this talk? What's the big deal? Well, there's several reasons actually. First is because coroutines are actually easy to use, which I think a lot of people might not be aware of. Definitely, I found them very intimidating originally when working with them, coming from other languages with other asynchronous programming patterns. I thought they were like super tricky and complicated at first, but once I got to know them, they're really not that bad. So I'm here to share that with you, help you understand why they're not that bad so that you can feel like they're easy to use as well. However, at the same time, they're also easy to misuse. I've found it's really easy if you don't know what you're doing to do things totally the wrong way, where you're not really getting the benefits from coroutines that you should. So I'm also here to let you know about that so you can avoid those kinds of pitfalls. Third, I think in general there's just a lot of confusing terminology around coroutines. There's just a lot of new terms. Frankly, I think a lot of the names are not that great. They can just kind of mislead you if you're not really familiar with what they mean. So I'm also just going to introduce that. I'm going to let you know exactly what all these new terms relating to coroutines mean so that when you read about them, when you discuss them with people, you know exactly what people are saying and you're not confused anymore. And lastly, there are some gotchas relating specifically to Kotlin Multiplatform if you're using coroutines, which I have figured out through trial and error and painful experimentation. So I'll let you know about those as well. So without further ado, let's jump into it. And first of all, I want to motivate why we even care about coroutines. Like why should you pay attention to this talk, and what's the whole reason for engaging with this new concept in the first place? And first of all, I want to go back and just think about how kind of traditional programming works without coroutines. So in this picture, we've got this thread, this line of execution. You can imagine this being like a CPU core that's running some code. And in the pre-coroutine world, how this works is usually with functions. If you want your thread to run some code, the code needs to be inside a function. So you can kind of put that function on your thread and it'll run it. And it'll run the entire thread, run the entire function, and when the function is done, then the thread is free again. You can run other functions on it, and of course this can be really complex. You can have the function running functions inside of it and stuff like that. But this is generally the traditional picture of how computing works. For example, if you've done iOS programming, this is how asynchronous programming is done on iOS. You define functions, and then those functions are dispatched to run on specific threads. But this is pretty limited. In particular, this limitation of the function has to run completely before the thread is free is very restrictive, because it means if we want any kind of work that is asynchronous, we have to split that up into separate functions. And a lot of ways that's kind of worked around is with things like callbacks, where you split your function into the function call and then the callback function, and then you structure it that way, but that's kind of a pain in the butt. So why we care about coroutines actually is because we want to use what's called suspend functions. We want to be able to write this kind of function that has specific points in it called suspension points, where the function can take a break and where you can set it aside, kind of pause it, and you can resume the function later when it makes sense to resume it. And so this is nice because it lets us structure our asynchronous code in a more intuitive way, where you can say, run this part of the function, here's an asynchronous suspend, and then the function can come back and resume. And it's all just, when you write it in code, it looks like one single continuous function, which is nice. So we really want suspend functions. And for an example of what that allows, if we took this picture here of like these function calls and imagine that they were all suspend functions, that would let us schedule these things in this way, where you can run part of the first function, then the latter half is suspended and kind of set aside in memory. Then we can start running part of the second function, set that aside. We can pick up the first part that we set aside, put it back on the thread, finish running it, and then we get this really interesting sequencing of events, which is nice for several reasons. Like, for one, we don't have to wait for something to completely finish before we start running other things. We can kind of make progress on parts of each task rather than just like having one task run completely. In general, it's really just a lot more flexible. So that's what suspend functions kind of unlock the ability to do this breaking up of work. But more specifically, like, okay, what is actually good about that? What is the quality of suspend functions? What's the reason to engage with them? Like, I get that you can do this thing, but why does that even matter? In particular, the keyword here is concurrency. So that picture I painted of breaking up the functions and kind of running them in the sequence, that is a concurrent scheduling of the functions, where even though we just have one thread and ultimately everything's running in serial, at least each function can kind of make a little progress before they finally finish, which is helpful because you can imagine maybe the first half of each of these functions is actually doing some important work that we want to get done. With this picture, they can actually all start some of that important work, and then they can finish later on. And so sometimes that's desirable in your software designs, that you have this idea of like multiple jobs that are each making a little bit of progress at a time. So concurrency is good in general. Suspend functions give us concurrency. If we actually also want performance improvements, where in general things are getting done faster, suspend also makes parallelism very possible. So you can imagine that same picture from before, but now if we have multiple threads in the picture, we can put those suspended chunks of code back on different threads for them to finish. And now you can see in this picture, thread 1 frees up in about half the time. So while the code is kind of finishing on other threads, thread 1 is now free to move on and start calling other things. And so in particular, like, imagine if thread 1 is our UI thread. This is really great, right? The UI thread is less busy even though we're running the same amount of code as we were before. So suspend makes it very easy, because if you start putting the suspended code on different threads, you suddenly get parallelism very simply without having to restructure your whole code base. There is kind of this scared face about thread safety. That's still a concern. Certainly, if these 3 suspend functions here are all kind of touching the same shared mutable state, there definitely could be like race conditions and locking issues and things like that. There could be deadlocks if they're interacting with like a mutex. So I'm mentioning this here only because suspend doesn't like magically solve that problem. If you think that somehow writing suspend functions means you don't have to worry about thread safety anymore, that's not true. So while it does make parallelism very easy, it doesn't solve kind of the common problems of parallelism that we all know about. So it helps with some things, but definitely it's tricky to write safe multi-threaded code even with suspend functions. So that's what's great about suspend functions, but maybe that's still not really clear. I think it's not entirely clear. Like, why do we as software developers, as app developers, why should we care about suspend? Okay, yeah, sure, concurrency and parallelism are great, but like, what are the real use cases where we really benefit from suspend functions? And I think there's 2 key ones that almost everyone deals with. So the first is, imagine sending some request over the internet, over like HTTP or whatever, and then getting a response. This is an extremely natural use case for suspend functions, because you want to be able to, in one place, write code that says, send the request, and then what do you do when you get the response back? It's really nice to be able to put those together in a single function. And you can do that with suspend, because you can put the suspension point between them, and then the function can kind of go to sleep, get set aside until the response comes back, and then your code can start running it again. Really simplifies the structure of dealing with requests and responses. Similarly, imagine you're loading some user interface. You want to like set all of that up, usually on the UI thread, and then it's kind of done until your backend has made some changes and maybe wants to update the UI. And then you want to kind of resume the UI thread, make whatever changes, keep the view up to date so that all the latest data is there. also a very natural case for writing suspend functions. You can put the suspend after the UI is loaded and resume it when there's more data to show on the UI. Again, greatly simplifying the structure of things. And these kinds of things happen all the time for, almost all common features that are added to apps these days. So you have a really direct reason to want to engage with suspend. If you avoid it, you're going to have to split these kinds of things up into separate functions, and the structure of your code is going to be less understandable. So I hope that finally this motivates why we actually want to engage with suspend. And now we have to kind of think back to the beginning. Well, where do coroutines come in? Suspend is great. Hopefully I've convinced you, but what is a coroutine? Why do we have to introduce this additional concept if all we really care about is suspend? Well, we have problems, actually, with the kind of simplistic picture that I've painted of how suspend works. There's a lot that we should be worried about, and let's go through some of those examples. So first of all, imagine I'm in this situation where I'm in my old non-suspending kind of traditional function, and I want to call a suspend function. How could that even work? Like, how is that even possible? Imagine if this green function could actually suspend, like we could set it aside and then resume it later. Well, because it's getting called from this blue traditional function, we would need it to be the case that when the green function finishes, we then pop back out of that stack frame back into our blue function and finish running the blue function. But that's not possible because the blue function is not a suspend function. There's no way for us to set aside the state of the blue function and safely resume it later. So it's totally unclear how this could even work, right? How do we get into the world of suspending functions from non-suspending? It's not clear. Another problem is this picture I painted of like setting aside these parts of functions on the heap. Well, usually when stuff's on the heap, there's some kind of sense of ownership, like some object is pointing to that memory on the heap so that we can make sure, that it's not going to leak, that the garbage collector can reach it and clean it up. Well, what is that owner in these cases? I definitely never specified that. It's again, not clear. There's even more problems. Imagine how exceptions work. Again, in our traditional case, right, if we're inside a function and an exception happens, well, the flow of execution kind of reverses temporarily, right? It's going to throw that exception back up the stack frame to the person that called our function. And if they don't catch the exception, it's going to keep going. It's going to throw it back to the caller of that function, right? It kind of bubbles up backwards up the stack. How does that work in the suspend case? Like, imagine we're in this situation now where the latter half of the suspend function throws an exception. Where does that exception go? We can't really throw it back to the caller of our function because since we're suspending, we've already moved on. That part's done. We're running other code now. We're running other suspend functions. And how do these even relate to each other? Like, should we not finish running that second suspend function because of the exception that happened in the first one? Again, unclear. What's even supposed to happen with this exception here? It's very vague. And that's not even it. There's still more. I showed this example before between concurrency and parallelism. Well, what if we actually care about that? What if that's important, that like we need all of our suspend stuff to run on the same thread, or we want it to run in parallel? If that's important to us, how do we even control that? Again, unclear. So suspend is not really enough. As nice as it is, as nice as the capabilities it gives us are, we need to clear up all this ambiguity in order to write reliable programs involving suspend. So basically, we need structure. We need more than suspend. We need stuff to help us understand how the suspend code is going to be working. And that's where coroutines come in. Coroutines are the structure for suspend. And there's two parts. So the first part is called a job, and this is the owner for suspend work. So anytime you're doing suspend stuff, there ultimately is some job that is the owner object for that suspend stuff. It has the ability to have like a parent-child relationship, so you can have sub-jobs of a parent job. You can kind of think of it like the stack frame for suspend work. So it is involved in handling errors, just like stack frames are with exceptions. And we'll go into more detail about this. But for now, that's the high level. The other part of structure we need is called a dispatcher, and this is the strategy for determining when the jobs are going to run and on which threads they're going to run. And that's it, actually. It turns out that these two pieces of structure are sufficient for solving all those problems I talked about before. They'll make it completely unambiguous how our suspend code should be working. And so what Kotlin does is it actually makes these a requirement. You have to have a job and a dispatcher for every single suspend call. There are no exceptions to this. There are cases where it might look like you don't have a job and dispatcher, but that's not true. You always have one. There are cases where it gets implicit, and it can be a little unclear if you're not sure, how it works under the hood, what the job and dispatcher are. So in particular, if you're already in a suspend function and you're just calling another suspend function, you don't have to specify anything about this structure. It's going to automatically reuse your existing structure. You'll get the same job, you'll get the same dispatcher, everything just works automatically. Similarly, in cases where you would normally have to specify a dispatcher, often you actually don't, because there is a sort of default dispatcher that will be provided for you. So it's confusing if you're unfamiliar, because it can look just magical how these things are happening. But once you understand, it's actually quite clear how this stuff is getting structured under the hood. So let's dive into a little more detail about how these pieces work and why they solve our problems. So first of all, let's kind of like repaint this picture now of suspend functions, showing how these new pieces of structure fix everything. So first of all, in our traditional function, if we want to call a suspend function, first we need a job, right? So we create this job object. It has a dispatcher as well, so that the dispatcher can decide like, hey, right now on this other specific thread, I'm going to run your suspend function. So we've cleared up that piece of ambiguity, and when that function suspends to memory or when it resumes, the whole time it's getting owned by this original job object that we created. So again, no more ambiguity there about who's actually controlling this code. And furthermore, if an exception happens, again, now we are clear, the exception can kind of trace back that job ownership, and we can say, okay, it's not really like thread 2 that is experiencing the exception here. That's kind of irrelevant. It's the job that experienced the exception. And so the nice thing about this picture is that as soon as we've created the job, our original function, our traditional non-suspending function, can immediately proceed. It can return, it can pass that job on to other things, and people can use that job to basically manage the suspend work that we have. So they can check, like, has it experienced an exception? Has it finished successfully? Maybe I want to terminate that suspend work while it's still running. The job gives us all that ability. And so hopefully now it's clear how this structure helps us keep track of things, and we no longer have to worry about our suspend code doing something that we don't understand. So how does a job work specifically? These mechanisms are important to understand in detail because you'll definitely be interacting with them. First of all, error handling. I think this is the most confusing thing about jobs. Basically, uncaught exceptions in jobs are turned into cancellations. There's this whole translation that happens. And before I go into the nitty-gritty details, the general intent, which you can pretty much trust, is that the whole thing with job cancellation is really just trying to be analogous to how exceptions normally work. So all the standard behavior of exceptions where like it's going to stop execution and it's going to like throw that exception back up the stack, basically that's how cancellation works as well. So the goal is that it should work intuitively, but specifically how it works is that when a job is canceled, a few things happen. So first of all, that job is immediately going to cancel any children that it has. And again, this is trying to sort of keep the analogy that like when you get an exception in normal code, it'll stop running further code in that function, right? Similar thing for jobs. You can think of child jobs as sort of like, additional code that's running. Of course, as soon as we get an exception, we'd want to stop that code from running. So that's why we cancel our children. The second thing we do is we check actually for a specific kind of exception. What kind of exception caused the cancellation in the first place? And if it was this specific type, cancellation exception, or some subtype of that, we actually consider that to be an intentional cancellation. This is the type of exception that is used, specifically to indicate that, okay, someone actually requested this job to cancel. In other words, nothing weird has happened. This is not really an exceptional case. This is fine. We just want the job to stop in kind of a non-noisy way. And if that's the case, if it was intentional, that's actually the end of it. So basically, all we do in that situation is we cancel the job, cancel the children, we're done. If it was not intentional, so it was some other kind of exception, that's actually an error now. That indicates, okay, something weird happened, something went wrong. In that case, it actually now cancels the parent. So the job will go up to its parent and give them the same exception to cancel them. And again, this is analogous to the exception bubbling up the stack behavior where, if something goes wrong in one function, we're going to keep throwing that up the stack until someone handles it. And that's basically what we're doing here. The one weird case that's kind of unique to jobs is that there is this idea of a supervisor job. And if a job is a supervisor, it will actually ignore cancellation from its children. And the reason why we want that is because specifically when you're talking about asynchronous work, there are often cases where you have sort of a parent job that's spawning sort of a bunch of parallel workers to do, a bunch of different subtasks. And we don't necessarily want it to be the case that any little thing going wrong in any one of those is going to cancel everything. That's not often what we want. So an example of this is like, imagine that some operation that the user is initiating involves like making two different web requests. Like maybe you have to update two endpoints in order to save their work. And if either of those updates fails, then the whole operation is no good, right? That would be a case where you don't want a parent supervisor job because you'd want it to be the case that if one request fails while they're both happening, we just consider the other one as failed as well. Whereas if you're doing something more like, imagine how most thread pools work, where you're kind of like giving work to some thread pool object and it's handing them out to various threads to get done. That's sort of your traditional supervisor situation where you would more want to manually check if anything has failed so that you can, handle that specifically. And so when you're dealing with cancellation, if you're going with a supervisor job, you are going to have to do some manual work. Well, unless you want to completely ignore your children having exceptions, you're going to have to save those job objects for your children so that you can do things like check for specific cancellation that occurred in them. But I would think that's generally rare. Usually you don't want a supervisor parent. I don't know. It depends on your application. So that's basically all the complexity about jobs. But in general, when you're making a job because you're doing some suspend work, how do you think through it? How do you decide which kind of job to get? Well, there's a few questions to sort of ask yourself. So first of all, if you're doing some suspend work, the first thing you should ask is, well, should this new work that I'm doing block my current work? And I'm putting that in quotes because in the world of suspending, nothing ever really blocks. You're not like blocking a thread, right? The work's just getting kind of suspended and put aside. But when I say blocking, I mean, am I just starting the suspend work and I'm waiting for it to finish? I'm suspending my function until that suspend work is done, right? If that's what you want, you don't need to think about jobs at all. That's kind of the simple default case where I actually just want to use the same job that I currently am. And the way you do that is you have your suspend function call another suspend function, right? I mentioned this before. It's the default implicit behavior that if all you want to do is call some suspend work and wait for it to finish, that's simple. You shouldn't have to think about jobs ideally in that case. However, if you don't want that, if you want it to be non-blocking, so to speak, but kind of part of your current work where it is sort of like a subtask that you're doing, right? That example I mentioned about like making web requests. That's where you want a child job, and you need some way to explicitly create a child job in that situation. That's where you have to do the manual job creation, basically, is if you want that truly asynchronous behavior where you're not waiting for the work to get done. When you're doing that, you also need to ask the follow-up question, should one exception in a child affect all the other children and affect me? If the answer is no, then you have to make sure that you're a supervisor before you make all those child jobs. And lastly, technically this is an option, right? If you answer no to that like, okay, it is non-blocking, but it's not really part of my work. I'm just kind of like spinning off this completely separate process that's going to run in the background. Maybe you need that. That is possible. And in that situation, it is possible to just kind of make a totally fresh job that is unconnected to any specific parent. And that would give you that, that result of this job is just this new completely independent background thing. You can do that, but you should be worried, basically, in that situation, because you're kind of explicitly saying, okay, no one is going to be tracking this job automatically, right? And you should probably figure out who is going to track it. Like, what if you need to cancel that work? What if an exception happens in there? Who's going to actually notice if an exception happens? When you do that, you need to make sure that you've answered those questions in some way and that you've figured out how you're going to structure your code to account for that. So now let's go into dispatchers in a little more detail. And there's actually only a few kinds of dispatchers you can even choose between, so it's pretty simple. First of all, there's a dispatcher that's literally called default. And this is basically a pool of background threads. You basically get one thread per core. And it really is just going to totally fairly dispatch your suspend functions to run on as many cores as possible. So it's going to make full utilization of all your resources, and it's going to just try to make sure that everything runs fairly. This is almost always what you want. If you're running some background work, it kind of just obviously does the right thing. Really, really simple, actually. You don't have to think too hard about it. And it's not just called default, it is the default. As I alluded to earlier, in many situations where you might think you need to specify a dispatcher, if you don't specify one, you'll actually get the default one. Because, like I said, it is kind of the obvious choice if you're just doing some asynchronous work. We also have a dispatcher called main, which is the UI thread, though in practice, this is actually pretty rarely used. There shouldn't be many situations where you need to use the UI thread. In the applications that I've developed, this is used in like one or two spots. Basically, if you have some spot that you know for sure is like updating the UI, that might be where it makes sense to say, okay, let's do this asynchronous work on the main thread so that we know that it's going to be safe to touch the UI when it runs. Third option is called unconfined. This is the I don't care dispatcher. It's kind of a greedy dispatcher. It basically says, when I want to run this suspend function, just run it right now on whatever thread happens to be running. I don't care. Practically, I've only found reason to use this in tests. It can be kind of nice in tests, and we'll talk about that later. But in production code, generally not a good idea. The main reason is because I don't care could mean, hey, I'm about to run this really computationally intensive thing, and I happen to be on the main thread. If you say I don't care, it'll just run it on the main thread, which is pretty bad, right? So in practice, I would avoid this one for production code for sure. Really not that useful. And that's basically it, actually. When it comes to choosing a dispatcher, generally, you don't want to specify. It's much better to, if you can implicitly, just inherit the dispatcher, again, by calling suspend functions. That's great. If it's not implicit, better to just like inject a dispatcher usually. You don't want to specify one. The one exception of that being if you need the main thread, just because the main thread is kind of special, it does make sense to specify the main dispatcher. I don't recommend using like dependency injection to inject a main dispatcher. That doesn't really make sense. You can hard code that one. But other than that, other than the main dispatcher, try not to specify your dispatchers anywhere. Make them something that is overridable, basically. And the main reason for that is testing, which we'll talk about later. So that's actually it for all the basic pieces of coroutines. Now you understand enough about how they work to understand all the terminology. So let's go through that, the official terminology that you'll see all over the place using the terms we've already described. So when people talk about a coroutine context, that is literally just the job and the dispatcher. It is the two required pieces of structure needed to run suspend functions. That's what the coroutine context means, nothing more. When they say coroutine scope, that is the context, so the job and the dispatcher, plus you get a name, which is really not important. It's basically just for debugging, which maybe you care about that. Plus you get some builders, which are essentially just convenience functions for creating child coroutines. So in all the ways that really, really matter, which in my opinion is the job and dispatcher, the coroutine scope and the coroutine context are really not that different. They're almost identical functionally. If you have a coroutine context in your code, it's very easy to get a scope that uses that context. If you have a coroutine scope, it's very easy to get the context out of it. So practically, these two things are nearly identical. It's really not a big deal distinguishing between one or the other. I find that a little confusing that they have these different names, but they're really not that different. But whatever, I don't know. That's how they decided to name them. Another thing you'll hear a lot is people saying structured concurrency. It's this really popular buzzword with coroutines. And essentially all that is referring to is, first of all, this requirement that you need a scope in order to call suspend functions, because a scope has the job and the dispatcher, which are the important pieces of structure. And second, that those builder functions have automatic sensible behavior, that they will automatically reuse your dispatcher, they will automatically give you a child job. And so basically what structured concurrency is talking about is that, as long as you are passing along coroutine scopes and reusing coroutine scopes and using the builder functions, you will naturally get this very nice structure to your suspend function, where every suspend call will have kind of a sensible parent for its job. You'll be using reasonable dispatchers. Like, it's not like all your code's going to run on the main thread. Everything will kind of work nicely. The caveat to this is it's actually very easy to avoid structured concurrency. In my opinion, way too easy. It's really, really easy in your code to just say, okay, make a brand new coroutine scope here that has no relation to anything. It has no relation to any parent job. It has its own dispatcher unrelated to whatever other dispatcher I have. It's really easy to make a brand new job. And it's really easy to basically opt out of structured concurrency, almost accidentally if you don't really understand what you're doing. This is a huge mistake that I saw when the developers that I work with first adopted coroutines. Is all over the place. People were just making brand new coroutine scopes. And essentially, as a result, we had no structured concurrency anywhere. So the important point here is that this is not really something you get for free. You really do have to opt in to structured concurrency. And once you've opted in, it's pretty easy to maintain, but you have to make sure that you're consistently making that decision to opt in rather than opt out. So definitely a huge pitfall about using coroutines. The last confusing bit is that contexts, and also the pieces of context, so jobs and dispatchers, all of these things can kind of interchangeably be combined using the plus symbol in Kotlin. So if you have any of these things, you can just say one plus the other, and what that's going to do is, if there's overlap between them, it will override the left-hand side with the right-hand side to form a new context. So I can say job plus dispatcher, and since those are two distinct pieces, it'll give me a coroutine context with that job and that dispatcher. Or I can say context plus job, and then it's going to say, okay, take the dispatcher from the left and then override the job from that context with this new job that I've put on the right. And so if you don't understand what's going on, this can look very cryptic, very confusing, but once you understand what it's doing, it is actually a very intuitive way to work with coroutines. It makes it very easy to control things like, oh, I want to do this thing now, but just with a different dispatcher. You can just kind of add that in, and you'll get the different dispatcher into your context. All right, and that's it for most of the confusing terminology. I think at this point you basically know everything you need to know about how coroutines work, but the talk continues. We're going to go into a lot of just practical tips about how to use this stuff, because it's definitely not obvious, I think, just from knowing the basics. So first of all, it matters so much which scope you use. This goes back to that thing about opting into structured concurrency. This is the most important thing of all. I think the pitfall here, what catches people, is you can be writing Kotlin code, you're in a traditional non-suspending function, and all of a sudden you want to call a suspend function, and the compiler is going to yell at you, and it's going to say, well, if you're calling a suspend function, you need a coroutine scope. And it is very tempting there, if you don't know what you're doing, to just make a coroutine scope and then call it. It's really easy to do that. That is almost always the wrong decision, because deciding which scope you're going to use is the most important choice when it comes to enforcing structured concurrency. If you have a coroutine scope like already sitting around that makes sense, you should absolutely be using that existing coroutine scope rather than making a brand new one. Almost never do you want to just like make something completely new. So basically, when you're calling your suspend function, always consider that scope, consider the job, consider the dispatcher. These are really important decisions that you have to consciously make every time. In particular with Kotlin Multiplatform, Android has its own coroutine scopes. For example, the view model scope. You want to make sure that you're using that scope in situations where that lifecycle makes sense, where that dispatcher makes sense for you. If you're working on other platforms like iOS, you're going to have to do some manual scope management. For example, in our iOS code, we have sort of like a parent scope for most of our Kotlin work. And that is sort of injected and inherited throughout the code base with various child jobs at certain points. So we can sometimes say like explicitly like, okay, cancel this scope. And we have supervisors at the right spot. So you have to think about what structure of scopes makes sense for your application, especially with Kotlin Multiplatform. And again, make sure that you're using those in the points where it fits your software design. When you do have to make a new scope, because it will happen occasionally, I mentioned this before, you have to think about lifecycle. Something has to be able to manage that scope. Something has to be able to do error handling. Maybe you want that scope to just run forever for the lifecycle of your application. I guess then it's simple. But if you don't want that, you're going to have some solution in place. If you do need to use a parent, who's going to be the parent? Again, important decision. Are you going to have a supervisor here? Think about how exceptions are going to be handled in your children. Is it testable? Great if your code can run in production, but are you going to be able to change the scope or the job or the dispatcher to run whatever test situations you need to test? And if you are relying on the main dispatcher, you don't have to worry about that. Again, I mentioned this before, you don't have to inject your main dispatchers because tests have a special way to do that. I'll cover that a little bit later with examples. But so important to have testable coroutines. I mean, tests are important in general, but asynchronous code in particular, right, very finicky, can be very tricky to reason about. You really want to make sure that it's testable. Good advice in general when you're writing your code, don't assume a particular dispatcher. For example, if your code really, really needs main, don't just assume that the person who's calling your code is going to already give you the main dispatcher, right? If you need the main dispatcher, it does make sense in your code to say, all right, explicitly get the main dispatcher here so that we can make sure that our code is running safely. That's always a good idea. And lastly, I've kind of alluded to this several times, if you're just in a suspend function calling a suspend function, everything's really simple. That's kind of the ideal case where you just don't have to think about all this coroutine baggage, right? So the more sensible suspend functions you can write, the less you have to worry about all this stuff with coroutines. The key here is this word reusable that I mentioned, where the caveat to writing a suspend function is you get this nice implicit behavior because you're essentially putting the responsibility of thinking about coroutines on the caller of your function. So whenever you write a suspend function, you're sort of implicitly saying, hey, it makes sense to call this suspend function in a variety of coroutine scopes, because that's the option that you're opening to people when you do that, that as long as anyone has any coroutine scope around, they can call your suspend function. So as long as that's the case, as long as it is this sort of reusable asynchronous code, just write a suspend function and then put the manual management of coroutines elsewhere in your code. That's much better than making all of your functions non-suspending and internally they're making all these manual coroutines to do their suspend stuff. We should also talk about these builders that I alluded to earlier. How do you actually use those? First of all, if you already have a coroutine scope and you just want to call some suspend functions, that's where the builders come in. And there's basically just two that you need to think about. They're called launch and async. And they both actually do the same thing, is that they start parallel work in a child job. Again, I think these are terrible names. I don't know why they're so different. They do literally the exact same thing. They start parallel work in a child job. The only difference between them is that async will give you the return value of that parallel work. So if you want the return value, use async. If you just want to start the child job for its side effects or something like that, that's where you use launch. If you don't have a scope, but you are in a suspend function, there may be situations where you want a explicit coroutine scope. So in particular, if you want to use like these builders and stuff, and there's ways to do that. So there's a suspend function just called coroutine scope that'll give you a child job coroutine scope, where then you can call launch and async and whatever. And it'll kind of just wait for all of that work to finish. And again, you don't really have to do much manual management. You can literally just call coroutine scope, do your coroutine stuff, and everything will pretty much work the way you expect. So again, the nice thing about being in suspend functions, don't have to worry about this too much. There's also a supervisor scope if you want that child job to be a supervisor. If you don't want the launch and async stuff to affect each other by exceptions. The other option you'll have, because again, if you're in a suspend function, you're in this sort of implicit world where you have no idea what kind of coroutine scope you're running in when you're in a suspend function. If you care, if you want to modify whatever context you happen to have around, there is this also with context function that lets you modify a part of the context to continue running your suspend work. Practically, you will almost always use this to override the dispatcher. You'll say, okay, keep whatever job I have around for my suspend work, but I'll switch the dispatcher for this work that I'm about to run. And technically, you could use it to override the job. It does work that way. Personally, I haven't really found any use cases where you would want to do that. Again, just going back to this issue of like, okay, who's going to manage that job then if you're overriding it? But you could do it. Maybe there are cases. And lastly, if you're in neither of those situations, so you're not in a suspend function, you don't have a scope, what do? You always have to get a scope. Step one, always get a scope. And again, going back to the previous slide, scope is important. Pick the right scope. Ideally, inject one that you already have. Make sure you have a good parent-child relationship. There is this just plain coroutine scope constructor. That's your last resort. If you need to get into the suspend world, you can always make a fresh coroutine scope if you can figure out the lifecycle question. Yeah. So finally, we can show some examples of how this stuff looks. So if we already have a scope around, this is what it looks like to use it. So in this case, I'm just assuming it's called my scope. And I'm showing examples here at the top of using those two builders, launch and async. So both of them work pretty much the same way. You call them inside the block. You can call whatever suspend functions you want. Both of them return you a value for managing that suspend work. The first one, launch, returns a job. Async returns something called a deferred, but again, deferred is literally just a job plus the value that is returned from the suspend functions. So I can also start other coroutines here that are going to wait for those first coroutines to finish. So this is an example of how you can kind of add dependencies between coroutines. So this first coroutine is just going to wait for the first one for the job to finish. The second example here is waiting for the async to finish, and it's also getting the return value out of it using await. These two types, job and deferred, are very similar in terms of like they can both be canceled. You can check for exceptions in the same way, for example. Another feature of these builders is that at the moment you call them, you can also use them to modify the context. So here I'm overriding the dispatcher for the work that I'm doing. So like if I need to like do a UI update asynchronously, this is a pretty common pattern of how that would look. And this last one here, this is probably more advanced usage, probably not going to come up very often, but just showing you how you can kind of work with these sorts of things. This is an example of explicitly creating a child job of the current scope that you have. So you can see I can access the coroutine context of my scope. From the context, I can get the job, and then I can pass that to the job constructor, which takes the parent job as its argument. So I've done this in like one case, so it's useful to understand how you can do this, but again, probably not going to come up very often. All right, how does it look working with suspend functions? So if we're in a suspend function, again, ideal case, normal case, you're just calling other suspend functions. So delay is like a built-in suspend function if you're not familiar with it. If I call the suspend function, it's going to use the same job, going to use the same dispatcher, and I'll just suspend until that suspend function is done. Super simple. Again, if I need to, or if I want to call launch and async in my suspend function, basically I need a coroutine scope to do that. I can use coroutine scope or supervisor scope to do that, and then inside that block, it'll create a child coroutine scope for me. In both of these functions, my suspend function will again suspend until those scopes are finished and all that work is done. And then lastly, an example of what it looks like to swap out the dispatcher for my current scope, whatever it happens to be. I can do that using with context, and I can keep calling suspend functions in there, but the guarantee that they'll all be on the main thread. All right. So moving on, some anti-patterns, some things to avoid, or some things that you can't use even if you want to. So first of all, run blocking. If you've ever looked at any coroutine tutorial online, you've seen this basically. Everyone uses it all the time, which is really annoying. You can't use it in Kotlin Multiplatform, so I recommend avoiding it for that reason. But also I think it's just kind of awful. It sucks because like realistically you never use it in production code. It's a really bad idea. So I find it really annoying that so many examples use it. So I think it's actually kind of a good thing to try to avoid it, just because it's better when your examples are more realistic. There is an alternative to it if you really want to use it that I'll mention later, but basically don't use it. The other thing is something called global scope. It is what it says it is. It is a global coroutine scope. This is technically available. It works with Kotlin Multiplatform. It's gross. I still recommend never using it. I think it would be extremely rare that you would want to use this scope, and even then I would recommend making it something that is injectable, even if you really do want it, just so you're not too tightly coupled to it. Just kind of an anti-pattern, because essentially this is one of the explicit ways to opt out of structured concurrency, which maybe you want to do, but it should be extremely rare. There's also a thing called new single thread context. This is interesting. It's essentially a way to get a dispatcher that always dispatches to a specific thread, not necessarily the main thread, which is interesting. Not available in Kotlin Multiplatform. I think this is actually okay though. Practically, I think where most people use this is where they want to not think about multi-threading. They don't want to worry about race conditions and locks and stuff. So if you were to use a new single thread context, you don't have to worry about that because everything with that dispatcher is going to use one thread, and it'll always run in serial. So I think this is kind of a blessing in disguise. It certainly makes your code more complicated, but it also forces you to write actual thread safe code, which is better if you can pull it off. So not too big of a loss here. Another one is actor. This is, if you're not familiar, it's essentially a way to do thread safe mutable state, but not available in Kotlin Multiplatform. I would tend to avoid it for that reason. All right, dispatchers IO. This one is pretty unfortunate. This one is something that exists only on Android. It's essentially a highly parallel IO blocked dispatcher. So for example, if you wanted to start like 1,000 different internet requests, that's actually really not that bad from like a software design perspective, because they're not gonna bottleneck on your CPU. They're gonna bottleneck on the network, which is not that bad. That's what it's designed for. Unfortunately, not available in Kotlin Multiplatform. So when you're writing your parallel code, don't go totally nuts with parallelism because you're kind of restricted to the default dispatcher. This one's really unfortunate. If you're making like a Kotlin Multiplatform library, public suspend functions are technically available. You can write them, your native code can call them. They are not necessarily thread safe. And basically that's just because when native code is calling into Kotlin, you don't have the structured concurrency requirement. It doesn't require that you have a coroutine scope and dispatcher available, because native code doesn't even know what those are necessarily. So yeah, I'm not even really sure how these work technically under the hood, but like I've talked to consultants from TouchLab before. They say, yeah, it might be safe, but basically you can't guarantee it. So might be playing a little bit with fire if you use these essentially. So my recommendation is, I think it is okay to use these if your software design really benefits a lot by having public suspend functions, especially if you're targeting Android. Great, introduce them, but you're still going to have to develop some kind of alternative for iOS. Basically going back to what I said before about life cycles and coroutine scopes, that you're going to need to make sure that there's some way to get a sensible life cycle for that asynchronous work for iOS to use if it's calling into a public suspend function. Some other rules of thumb, basically some things to look for, like if you're doing buddy coding or code review, some things to look for. Never specify a dispatcher. Pretty simple rule. The asterisk is because of the main case. There are cases where you want the main dispatcher. Then it's okay to specify, but 99% of the time, probably don't want to specify a specific one. Never use these coroutine scope or job constructors, because those are basically the easy ways to opt out of structured concurrency, so don't use them. You'll be a lot safer if you don't use them. Asterisk, because there are very rare corner cases where you do want to use them, where, like I showed that example of manually creating a child job. Maybe you do want them, but should be extremely rare. Again, 99% of the time, don't use them. Never use this coroutine scope by. I'm not sure how common this is, but at least when, my teams were first adopting coroutines, we use this all over the place, basically adding conformance to coroutine scope using delegation. It's very convenient because what it does is it turns your entire object into a coroutine scope, which means if you want to do things like creating coroutines, it suddenly becomes very simple because you can just directly call all of those methods. In retrospect, actually a terrible idea, because the main problem is, sure, it gives you all that convenience, but it also means that now your object is essentially exposing its coroutine scope publicly, that anything with access to your object can use its coroutine scope to do stuff, which I think is not really what you want most of the time, right? Most of the time when an object has a coroutine scope, it should be kind of an internal thing. If that object needs to do asynchronous work, that's what its coroutine scope is for. You wouldn't want outsiders to be reusing your coroutine scope for things. So I generally recommend avoiding this. The asterisk is because maybe you are making an object, you're making some kind of custom coroutine scope, then sure, it's fine. But in most cases, that's not what I've seen. In general, if you're looking at how jobs are working, there should just be some reasonable parent for job ancestry, like again on Android, like leading back to the view model, or if you're on iOS, you should probably have some kind of manual job ancestry that you're creating where there's like supervisors at certain points and there's these natural positions where you can do cancellation and stuff like that. You have to have some kind of sensible job hierarchy in your code, whatever that happens to be. So finally, let's talk about testing. How does that look? Basically, you use dispatchers. When you're doing test code, if you can mock the dispatcher, that will get you everything you need in order to test asynchronous code. Jobs, you don't have to touch. You should be able to use like the normal jobs that your code normally uses. You just have to mock the dispatcher. So most important rule of thumb, never ever use real dispatchers in tests. You should never be using dispatchers.main. You should never be using dispatchers.default in your test code. You should never be like injecting those into your test code to run them on the real dispatchers. What you should use instead is a thing called test dispatcher. This is in the coroutines test library. And what this does is it uses a virtual time, not wall clock time, to prevent delays. So if your dispatcher encounters a coroutine that says delay for so many milliseconds, what it does is it just advances its virtual time to act as if that delay has already happened, and it actually runs almost instantaneously. So this gives you a few great things. First of all, it Obviously, your tests run faster. You don't have to wait for real delays and real timeouts to occur in your code. But most importantly, it gives you a lot more reliability because you can control that virtual time to do exactly what you want in your test. So you have two options when it comes to using Test Dispatcher. You have the standard Test Dispatcher, which is this manual control option. And when you first start using this, it might seem like a huge pain in the butt because basically everything that you would expect to just run asynchronously, you don't have to do anything. Now you have to really deliberately step through it with manual control. So in particular, some pitfalls here that might catch you off guard. If you just start a coroutine with the standard test dispatcher, it won't run because virtual time is basically paused, and you have to explicitly say like, okay, actually run the coroutine that I just gave you, or advance virtual time by so many milliseconds in order for anything to happen. And like I said, that might seem like a huge pain in the ass, but when it comes to testing, it's actually awesome. It's really, really great, and you should come to embrace that and see it as great because what it does is it gives you that reliability that, when you're testing asynchronous code, at least the experience I've had, it can be just rife with unreliability where you get flaky unit tests where it's really hard to test the specific corner cases that you want. This gets rid of that, right? It gives you that ability to do very fine-grained control. So you can say, okay, what if this async thing runs right before this one runs? And you can test all the specific situations that you might be worried about in your async code. So definitely more verbose, a little more work, but the reliability, the results, the test coverage you'll get out of it is excellent. So definitely worth the effort. The other option you have, this is finally coming back, the unconfined test dispatcher. This is, again, the sort of like greedy, I don't care dispatcher. So it will run things automatically. You can just give it a coroutine and it'll run it, but as a consequence, you will lose all control of threading and order. So you might have to worry about that reliability that I was just talking about. But it turns out there are situations where you want this, where you're just testing some asynchronous code and you're not really worrying about the corner cases. You just want the asynchronous code to run so that you can see what the result was. That's where unconfined test dispatcher is useful. I'll show an example of how that works. I also mentioned this earlier that if you are specifying the main dispatcher in your code, that's fine. Tests have a specific way to override that, the set main, reset main. You can inject a specific test dispatcher to use. So you can set a standard test dispatcher and you can manually control the main dispatcher that way. You can inject an unconfined dispatcher to just make all the main code run greedily. It's your call. But again, if you're following my advice here, you shouldn't need this that much. You really shouldn't have a whole bunch of places in your code that are tightly coupled to the main thread. At least the way that I've done it in our code is I've tried to only have main in like a few specific spots, test those specific spots, and everywhere else just inject dispatchers and use kind of like generic dispatchers. And that way, all of your tests, for the most part, can just avoid this whole set main, reset main complexity, which is nice. So how does this actually look? How would you do this stuff? So first of all, creating a standard test dispatcher is super easy. You can just call it. I can then pass that onto a coroutine scope. This is one of the cases where it's fine to construct a coroutine scope because I'm just in a test case. It's fine to kind of opt out of structured concurrency in this situation. And then I can use that test scope to launch a coroutine, and I'm just gonna simply here like delay a little bit, change the value of this variable and delay a little bit. And how it might look to test this, you can see I can advance the virtual time by a specific number of virtual milliseconds. I can see that the variable is still false. And then I can, I could keep doing that. I could advance time by another 50 milliseconds and see what happens. It also has this thing, advance until idle, where it'll basically run the coroutines as far as it possibly can. And so I can call that should finish everything, and then I can see that the variable has changed values. So really not that bad. An example of where unconfined is useful. I'm kind of cheating here because I'm using a concept I haven't introduced yet, which is immutable state flow. But putting it really simply, this is an object where you can emit values from it, and something can subscribe to see those values that are being emitted. So what I'm doing in this test here is I have this list of observations that I'm going to collect. I start a coroutine with the unconfined test dispatcher. So I'm using that syntax to override the dispatcher from my test scope. So I launch this with the unconfined test dispatcher, and I collect the values emitted from that flow, which again is going to kind of do it greedily. That's the goal here. Then I'm going to launch another coroutine, which is emitting the values. I have to do this in coroutines because collect and emit are suspending calls, so it's a requirement of structured concurrency to do it in a coroutine. Then finally, I just say advance until idle. Again, run everything until there's nothing left to run, and then I can assert that I've seen all of my observations. So this is one of those cases where, again, I just kind of want to run everything, let it all run, and then see what happened. That's what unconfined is useful for. An interesting question here, I think a good thing to consider is what would happen if I did not use unconfined test dispatcher? So in particular, think about if I removed that, then I would have just testscope.launch in both situations. That means both of these coroutines that I'm launching here are using the same dispatcher. They're using the one from my test scope. So try to think about what would happen in that situation. Why might this test fail in that situation? If you want to think about it, feel free to pause here. But now I'm going to tell you the answer. So the reason why this test would fail without unconfined test dispatcher is because that scheduler for the test dispatcher is not guaranteed to run in any particular order. It could, for example, choose to run that second coroutine, the emit, completely before it goes back to resume any of the collect calls. And specifically with a mutable state flow is not guaranteed to give the subscriber every value if they're not collecting quickly enough. So that's kind of where you might have to be familiar with the object here. So essentially, in that situation, if the scheduler runs emit, the subscriber is not collecting quickly enough because it hasn't been resumed at all yet. So when it finally resumes, it will only see that final value. So the results would actually just be 3.6. It would only collect the initial value, which was from the constructor, and then the very last value. And so unconfined helps here because it turns it into greedy collection, right? Where as soon as we have a value available to collect, it's just going to run that right away on the same thread, which simplifies the test case significantly. We don't have to bother saying emit, then collect, emit, then collect. Unconfined solves that. All right. Practically, how would you actually test things though? Those were kind of toy examples. What would we actually write? I was kind of going into nitty-gritty details there just to make sure everything was more explicit. That's not really how you would write things. There's actually this thing called test scope, which is probably what you're going to use 99% of the time. Test scope, it automatically gives you a standard test dispatcher. It also has some implicit behavior, like if you've been using set main, it'll actually use the same dispatcher as that so that you can use one dispatcher for all of your code. It's nice, basically. If you're in your simple testing situation, it'll give you everything you need. If you need to do complicated stuff with multiple dispatchers, that's where you maybe want to be more explicit, but test scope should get you there most of the time. There's also a thing called run test, and essentially this is a function that gives you a coroutine scope and it will wait for all the coroutines to finish. It'll give you a built-in test dispatcher, by default standard. The caveat is that behavior of waiting for all coroutines. So in most cases, that's probably what you want. You want to run your coroutines, and you want to make sure that though they aren't getting into infinite suspend loops where they're just suspending over and over forever. That's often not what you want in your code. And run test very nicely has a built-in mechanism for handling that. It has a built-in timeout so that if the test runs for, I think, 60 seconds without terminating, it will consider the test as failed, which is nice. There are some situations where you don't want that. For example, you can start coroutines that intentionally never finish, where they're just running forever in the background. Run test will fail those cases because it will see hey, there's still this coroutine running, and I am tired of waiting for it. So if you need that, basically your options are you have to, in your test case, manually cancel those endless coroutines. so that it won't time out, or you just don't use run test and you kind of use the more manual management that I showed earlier. So in general, run test is most useful, I would say, if you're just testing suspend functions, because it just gives you that scope so you can start calling suspend. It's useful in other cases. It's kind of a case-by-case basis. You could decide if it makes your code nicer or not. I'll show examples of these. And this is the alternative to run blocking that I recommend you try out. So if you want to screw around with coroutines just to see what happens, write unit tests, and then you can use run test as an alternative to run blocking. All right, so how do these look? This is the realistic case that you should pay attention to. So cleaning up that first test that I showed, we can just call test scope. We don't have to specify all this dispatcher crap. I can use the test scope to launch still, and then the nice thing is this virtual time control methods are available directly on the test scope. I don't have to like dig into the dispatcher like I did before. Super clean, super simple. In my experience, this is what 90% of your test cases are going to look like. You'll probably make a test scope. You'll maybe inject that test scope into an object and start calling stuff on it, and then you'll just use these advanced methods to test whatever you want. Using run test, we can clean up that flow example as well. So most of the time it's going to look like this, where your test function equals the call to run test. And run test implicitly, just this is set to the coroutine scope. So you can see now when I'm launching my coroutines, I can just directly call launch. Very, very simple. I can also directly call advance until idle. I don't even need an explicit receiver. So it does make the test code super clean. The caveat here is those endless coroutines. So flow.collect is endless because you're basically saying collect this flow, observe the values coming out of the flow until I tell you to stop. So it is an intentionally endless coroutine. So in order to make this test not time out, I do have to explicitly save the job I got from launch, and then after I'm done with all of my assertions, I have to explicitly cancel that job. Otherwise, it would fail every time. All right, so that's actually it for most of the coroutine stuff. I do have this kind of addendum section on asynchronous data structures. Probably just, these are useful. You're probably going to interact with them, so I feel like I should cover them. And these are basically data structures where you will need a coroutine scope around in order to interact with them because they have suspending functions that you're going to want to call. The caveat to all these, I'm not really going to get into the structure of this, but if you're using them, they're great. But if you're targeting non-Android platforms, you'll need some kind of wrapper because, again, you need a scope to interact with them, and non-Android platforms don't understand how scopes work. So they can be a great alternative. Like I'll say explicitly in the code that I write, we do this. We basically expose some of these structures publicly just because they're nice, but then we also provide public alternatives for our iOS code. So first one is called flow. And basically what a flow is it emits a sequence of values suspending between each value. That's all it does. In particular, I kind of hate this name. I think it sucks. I think it would be much better if they called it like a suspending sequence or something like that, because at least in my mind, when I hear flow, I imagine, all right, there's like this flow of data that's just flowing along, and I can start observing that. I can subscribe to that flow and start seeing what is flowing, and then I can stop, and it's going to keep flowing. No, flow does not actually guarantee that at all. It could work that way, or it could not, basically. It's a very weak guarantee that this interface provides. So in particular, if all you have is one of these flow objects, you probably shouldn't assume that it's like actually flowing data. You should assume it's kind of like a lazy, some people say cold flow, where basically maybe it only does anything when you say, hey, like, do you have any values? That might be at that very moment when it says like, okay, fine, I'll like compute something for you and give it to you. Because that's sort of like, in general, the weakest assumption you should make about it. That's the safe thing to assume. And in fact, there is this built-in function called flow that builds a flow object, and that's exactly how it works. It makes one of these lazy flows that's only going to run code when someone actually asks it for a value. So pretty weak in terms of like the sort of functionality it provides, the kind of guarantees it gives. I haven't found a lot of use cases for it, but it's basically like if you want a suspend function that returns a sequence of values, yeah, this is perfect for that. But again, only in that really lazy situation where that's all you need, which in my experience is rather rare. So upgrading from that, we have what's called a shared flow. And this, in my opinion, is something that actually flows. So if you have a shared flow, you can actually write code that can just like loop through and emit values. And you don't have to care about whether anyone's subscribing to it. You can say like, okay, emit, 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 emit. So you can have, in my mind, a more logical sense of like, okay, this is actually like a flow of information, regardless of if anyone's watching me. The catch, and this is a very important, confusing catch, is that you have to suspend every time you emit a value by default, if you're kind of doing the naive thing with shared flows. And the reason for that is because a shared flow does not guarantee any kind of storage space. And the reason why that matters is because if you're writing that kind of code that is like looping through and emitting values, right? If I emit a value and then I want to continue looping and emit another value, how do I guarantee that that first value is actually going to get out the door, that someone's going to see it? I have to actually suspend to wait for a subscriber to come along and grab that value from me. And once they've done that, then I'm free to continue and I can emit another value. So there's kind of a catch here because on the one hand, you can write your code in such a way that you're looping through, suspending and emitting values, and it looks like you're just kind of flowing. But in reality, by default, it is sort of like a synchronized process where you do actually have to wait for someone to come along and grab a value before you can proceed on to emit the next one. So that can definitely be confusing. Especially confusing about it is that a shared flow does have a method called try emit, which is not suspending. And if you read the documentation for it, it basically says like, oh yeah, like if you have a subscriber, emit the value to them. If you don't have a subscriber, it will fail because there's no one available to get the value. The caveat here is because it's not suspending, by default, try emit will always fail, even if you have subscribers. That's the really confusing thing. And the way to think about that, I think the most intuitive way is, right, even if I have subscribers that are ready to accept values from me, and I call try emit, which is not a suspending function, again, it has no guarantee that I'm actually going to be in sync with my subscriber, that they're going to be ready to handle that value because I'm not suspending specifically. So that's why try emit will always fail, even if you have subscribers, because it's only the suspend call that can guarantee that like, oh, I can like pause me, I can resume the subscriber, give them the value, and I can make sure that everything is going to stay synchronized. So by default, if you try to use this with try emit, definitely not going to work for you. Basically, you have to dig into the more advanced values. You can configure a shared flow to have a buffer, to explicitly say, I'm giving you such and such storage space so that you can hold on to a few values independently of someone actually coming along to subscribe and collect those from me. So then try emit can work if you're doing a buffer. You can also have the option to replay. So if a subscriber shows up late, you can kind of like catch them up a little bit. The caveat there, though, is like then you run into even more corner cases. You have to worry about like, well, what if the buffer overflows? Like, what if the subscriber is not keeping up with my emitting? It definitely gets complicated. So you can basically, with a shared flow, you can get that more active flowing behavior. It gets a lot more complicated, though, because you have to kind of think about this synchronization issue. So upgrading from that again, we have a state flow, even more advanced. And basically, it's just a shared flow with a single buffered value. That's all it is. But this actually provides a lot of benefits, a lot more power. So in particular, once you have a state flow, you never need to suspend anymore. You can suspend if you want, but you don't need to. Because, you know, as a subscriber, sure, you can subscribe and say, tell me when the value changes, when a value is emitted. But you also don't need to, because since there is that guarantee of a single buffered value, as the subscriber, you can also just say, well, tell me what the latest value is. And you don't have to suspend to do that. Similarly, as the emitting side, you don't have to suspend on emit and synchronize with your subscriber. You can just say, just change the latest value. It's not a suspending call. Very simple. Even better, all of this is thread safe. You can have two different threads both checking and setting the value, and you don't have to worry about anything. There are some limitations though. You don't get all of this for free. That would be too perfect. So first of all, you cannot emit a repeated value. That's not what a state flow is designed for. So like if I have a flow of numbers, right, I can't say emit 3, emit 3, emit 3. My subscribers will not see that because basically from the perspective of the state flow, if the latest value is 3 and I say set the latest value to 3, the state flow says, well, actually nothing has changed. So I'm not going to tell anyone about that. The value has remained the same, so no value is emitted at all. Which you could see as a downside, or you could just see as like, if that's what you want to represent, if you want to represent kind of a latest value, that's exactly what a state flow is good for. In particular, it's sort of about an eventual consistency, because if you're also doing like a bunch of like repeated updates where you're saying like changing the value very, very rapidly all the time, subscribers may not see all of that. And that kind of goes back to the example I showed before in the unit test, right, where one collector wasn't collecting quickly enough, so they just saw the first and last value. That's, again, a limitation, or you could say a feature of the state flow. But if that's the situation you're in where essentially your subscribers only care about like, okay, eventually I want to get the later values. I want to be eventually consistent, getting eventually what the latest value is, then that's probably fine for you, as long as that's the situation you're in, if that's what your software design calls for. So really powerful, but also limited in some ways. And a key point I want to call out here, because I definitely found this very confusing when I was learning them. You have these three objects, flow, shared flow, state flow. Their names are similar. I think their use cases couldn't be more different. It's like night and day, such a huge difference between flow, shared flow, state flow. Frankly, I think their names should be a little more different to help you understand that. You should be very, very careful when you're choosing them. It's a very important distinction, because this whole idea about like, do I care about every single value that's emitted? Do I care about synchronization? Do I care about whether it's lazy or whether it's hot? All of these are really important distinctions between them. Upgrading or downgrading from one to the other can completely change the behavior of your program. It's such a big deal. I'll also talk briefly about channels, just because you might run into them. And basically what a channel is it has one sender and one receiver, and it can be buffered. And you might look at that and say, that sounds very similar to a shared flow. Why does this object even exist? What's the difference? There is a key difference here. In particular, it's that one receiver thing. That's the big point. So if you have a shared flow, and it is shared across multiple coroutines, all of those coroutines can collect the flow, and they will see the values emitted from that flow. In contrast, a channel, if you share that one receiver, it still kind of acts as a single receiver, in the sense that if I send one message to that receiver, only one person will get it. So even if 3 coroutines are all collecting on that one receiver, it's not that they all get that message. Only one of them will get each message that I send. So in particular, you can use this as a kind of distribution mechanism, where if you have a bunch of coroutines and you want to distribute messages across them, a channel is exactly the thing you want in that situation. However, I would say that's just about it. That's the only reason why you should choose a channel, is specifically for that use case. If you don't need that, if you want all subscribers to receive every message, or if you're just not sharing it, if you're just having like one sender and one receiver, don't use channels. Just use flows. They're so much simpler. Use whatever kind of flow makes sense in your situation. They're just much easier to interact with than channels are, frankly. And that's basically it for the talk. So it's been a long talk. In summary, I will say these are the main takeaways I want to emphasize. So important to carefully choose your coroutine scopes. It's the most important decision you make when interacting with suspend functions. Don't use real dispatchers in your tests. There are ways to make it work, but it's an utter nightmare. So much harder to test the cases that matter. Start using those test dispatchers and your life will become better. And I don't know how important this advice is in general, but at least for my teams that I work with, we don't use suspend very much. it's kind of hard to get into the mindset if you haven't been writing a lot of suspend functions to start writing suspend functions. So I know that we've definitely shied away from it. And as a result, if you look at how our code base works, we basically have just like a few suspend functions, and then we have tons of places that are creating coroutines to interact with those suspend functions, which I don't think is ideal. I suspect you want a more balanced approach, because suspend functions are nice. They give you this very simple implicit behavior. They're more reusable. So if you haven't been writing suspend functions, if you're not in the practice, I think it's worth trying to really consider that, like, hey, should this be a suspend case? Should I kind of push that responsibility of working with the coroutines somewhere else and make this a more reusable chunk of asynchronous code that anybody can call? I think there's definitely a lot of benefit in trying to leverage that more. Even if like you're just making them private, right? If you have an object that is doing some asynchronous work, maybe try making a bunch of like private suspend functions to do the bulk of the asynchronous work, and then just have like a single place that creates the coroutine to start the suspend calls, rather than having a whole bunch of non-suspending functions with all these coroutines inside them. I feel like the former case is probably going to be easier to reason about. So that's it. That's my whole talk. If you've got any questions, you can ask in the comments. Maybe I'll get around to it if I notice. And yeah, I hope that was helpful.